Okay. Good morning, everyone.
Good morning, everyone.
Let's perhaps wait
Perhaps
a few more minutes.
in a minute,
People to, uh, participants to collect and start.
start.
Good morning,
Good
everyone.
morning, everyone.
Krishnan, we are on.
We are
We are in the
we
keynote
are in
session.
the keynote session.
Okay.
Okay, so
Team, good morning again,
good morning
and
again,
a warm
and
welcome
a
to
warm welcome
day
to
two,
day two,
9
nine,
IEEE International
IEEE
Conference on Cloud Computing and
Cloud
Emerging
Computing
Markets.
Emerging Markets.
We have an
We
exciting
have an
session in
exciting
front of
session
us.
in front of us.
We'll start the day
We
with a
start the
keynote
day with a
from
keynote
Dr.
from
Rama
Dr.
Govindarajan,
Rama Govindarajan,
who is Director of
who is
Engineering
Director
at
of
Google,
Engineering at Google,
who will join us
who
from
will
the
join
United
us
States.
from the United States.
We will then
We
have
will
a
then have
art
a
paper
art
session
paper
where
session
three
where
papers will
three
be
papers
presented,
will be presented,
after which
after
Andrew
which
Hashka
Andrew
from Google
Hashka,
Australia
Google
will
Australia,
offer us a
will offer
tutorial
us a
session
tutorial
around
session
application
around
modernization.
application modernization.
So a very
A
interesting,
very interesting
information-packed session
fact
away.
session away.
And let me start
And let me
by
start by
warmly welcoming Dr.
warmly
Rama.
welcoming Dr. Rama.
Dr. Rama is a
Dr.
director of
Rama is a
engineering at
director of
Google,
engineering at Google,
where he leads
where
the
he leads
system
the system
infrastructure performance
infrastructure
engineering team.
performance engineering team.
Prior to that,
Prior to that,
Rama is a distinguished
Rama is a
engineer at
distinguished
IBM,
engineer at IBM,
responsible for leading the
responsible for
software
leading the
at
at
IBM's
IBM's
supercomputing lab,
supercomputing lab,
where he led the
where he
development of
led the
next
development of
generation
next generation
supercomputers.
supercomputers.
Dr. Rama received
Dr.
his
Rama
MS
received
and
his
PhD
MS
in
and
computer
PhD in
science from
computer science from
Rensselaer Polytechnic,
Rensselaer Polytechnic,
and he did his
and he did his
bachelor's in engineering in
bachelor's in
computer
engineering
science
in
from
computer science from
Birla Institute of
Birla
Technology,
Institute of Technology,
Ranchi, India.
Ranchi, India.
Welcome again, Dr.
Welcome
Rama.
again, Dr.
With
Rama.
you.
With you.
Thank you, Sri Krishnan, for the warm welcome. I hope everyone can hear me and can see the slides. I'll get started. I have a lot of material to cover, and I hope you find this interesting. The key messages that I want you to take away from this talk, and I'm hoping by the end you'll be convinced, is the transition to cloud has huge advantages, and I would encourage everyone to seize these opportunities, and I'll go over the details here. To really leverage cloud efficiently, there is a need for much cleaner abstractions to make it easier to transition to the cloud, and I'll talk a little bit about that. The other key trend that I want to alert everyone to is deep learning has really emerged as a breakthrough technology that can solve many hard problems that were previously thought to be, beyond the reach of technology. And these have great relevance to the emerging markets. Many of these technologies can actually solve really hard problems that are pressing problems in emerging markets. The other point I want to sort of help everyone understand is the need to leverage frameworks. There are a lot of frameworks that exist to rapidly develop applications and infrastructure. And so leveraging those is very important. There's also an increasing trend of using accelerators, especially with deep learning, and making use of them to solve hard problems is, I think, an important key trend here. The other things that are sort of very important for the Indian context is the need to develop good data sets and sort of continuously build on and add to the data sets, curated data sets that are sort of well labeled is very, very important, which is ground truth. And also building sustainable functional flows that allow you to grow on your capability with sort of a constant improvement with new data being added to the system and new learning based on simple machine learning models. So those are the key messages that I'm hoping to help convey to you in this talk here. So I've organized this into 3 parts. The first part I'll talk mostly about the trends that are going on and what they mean and why the transition to cloud is inevitable. The other is the second part of the talk will be more focused on sort of opportunities that exist for emerging markets like India. So since this is a cloud computing conference for emerging markets, I think that is particularly relevant. And the third part, I'll talk a little bit about how can one prepare themselves to seize on these opportunities and make advances to solve real problems. So first, let's talk about trends. So one of the trends that you see, and this is a little bit dated, it shows the networking capability at Google. And I'm using Google just as an example because that's a good data point that I have access to. And it shows you the bisection bandwidth of the data center networking that has been available since 2004 to 2013. And this trend continues. And the key message here is if you look at the y-axis, which is a log scale, the networking bisection bandwidth capability has increased by a factor of 20x in 10 years. So what it means is the pace at which networking capability is increasing is much faster than compute capability. The next trend that you see, and here is a good example, is if you look at how CPU performance has improved, which is the blue line, over time in this last 10 plus years, is not as fast as the data sets that are growing. And the data set, the red line here, is only from YouTube. In YouTube, you have users uploading video of up to 11 hours every minute. So in each minute, 11 hours of YouTube video data gets uploaded. So the data sets that are growing, and this is just one example use case, is at a much faster pace than compute. The other example is also Google Photos, and Google Photos currently receives more than a billion. It has more than a billion active users. Over a billion photos get uploaded every day, right? And the photo quality is also being increased, and the demands from end users is for very high resolution photos and high resolution videos. So there's a need to be able to manage this kind of data sets in a manner that is easy to operate on, easy to manage, easy to sort of do various operations on. So there's need for infrastructure to enable that kind of growth of data sets here. The other key growth point is the growth in machine learning applications and research. So the first graph shows you the number of machine learning papers in arXiv, which has been doubling every 18 months. If I look at Google directories, which are related to machine learning, the source code is doubling every 18 months. And if I look at the compute capability that is needed to train models, that is doubling every 3.5 months. So you can see the pace of progress and the pace of computing demand is just astronomical in this space. And the reason is because this area in particular has been delivering huge breakthroughs, right? And that's the reason why these are growing so fast here. So these industry trends sort of point to some important things, that there are new kinds of applications that are sort of starting to dominate the computing space. Streaming services, machine learning and AI applications, social networks, video conferencing. Given these pandemic times, we are having a conference under video conference. So this has been growing exponential. All these are growing at exponential rates. There's an exponential rate in growth in data sets. And there's a need for infrastructure that can manage this kind of scale efficiently. And sort of the obvious tools are, MapReduce kind of frameworks and data analytics kind of frameworks, right? The other sort of interesting trends in systems that you see is, and this is sort of the left side graph is showing you the various processor generations of different vendors. And what you see is the bandwidth, the memory bandwidth is on the blue line, and the compute capability is the yellow line, and the inter-socket bandwidth is on the red line. So one obvious thing that you note is, although compute and memory bandwidth are scaling reasonably well, the inter-socket bandwidth is not scaling very well, which means that there is a bifurcation and there's more complexity and more heterogeneity in the computing capability that is being offered. And then on the right-hand side graph, if you look at accelerators, the accelerator compute performance is skyrocketing, but its memory bandwidth is not keeping up, right? So there are some challenges in how you leverage this increased computing capability, because all parts of the system are not growing at the same scale. Therefore, there is imbalances that are being created, which makes programming the systems much, much harder. Right. So the next trend that you see is the memory and interconnect trends. So on the left-hand side graph, you will see the CPUs versus the accelerators and some example accelerators that I have, and the bandwidth that they have access to, right? And this is coming through HBM and other technologies that are there, or SRAM. And also the memory capacity is another issue. The moment you try to scale both memory capacity and bandwidth, you fail to do so. You see CPUs have great memory capacity, but they don't have the kind of bandwidth that accelerators need. But when you have accelerators and you have high bandwidth to them, you don't have the kind of capacity to sort of sustain that kind of computing capability. So there's huge number of imbalances that are being created that need better techniques and technologies and frameworks to leverage the full capability of the underlying system, because the balance is changing. And there's also one other point is these accelerators are typically attached through I/O interfaces, and those I/O interface performance is not improving very much. So the penalty to sort of handshake between the accelerator and the host is also increasing dramatically. SRAM is another example where scaling is a big challenge, even with improved process technology. And so what is clear is the approach to try and fit the entire working set into SRAM is just not working. So you have to deal with memory hierarchies. And somehow the frameworks have to be developed, and the compilers and the software technologies to hide this kind of complexity and the various levels of the hierarchy in programming the systems to realize their full potential. What we also see is the accelerators in the data centers are growing very rapidly. So in just 4 racks, we can now pack about 11.5 petaflops. And this is like 4 years old, right? So I'm confident this is now at least more than 2 times that. So the compute capability density is also increasing when you have these kind of accelerators to solve some of these hard problems here. What you also see is you have a varying set of workloads and a varying set of underlying platforms. Right? You have CPUs, you have GPUs for graphics and sort of machine learning workloads. You have tensor processing units to operate on tensors and vectors for machine learning. You have FPGAs for various kinds of acceleration. And the next version of accelerator, which will have question PU, which you can sort of put in your own, which one's for transcoding or what have you. Right? What it means is to get the next version of this question PU, you need much tighter hardware-software co-design. You need to understand the workloads. You need to understand the characteristics to sort of understand what is the next set of accelerators we should build. What is the methodology by which we'll be informed of these next set of accelerators? The other point also is in a given data center, you will have a variety of workloads. Even just at Google, we have more than 200,000 applications and services that run on various platforms, right? So each one lends itself to much more efficient execution on some of these. So you have a heterogeneity of platforms available and a vast number of application use cases, and being able to map them to the right underlying platform is an important abstraction that is needed here, right? And it also sort of suggests that no one center can have all capabilities, right? So if you are a small organization and you want to have the ability to leverage all these technologies, the only way to really get them is to transition to the cloud. And it can be any cloud. It doesn't have to be Google Cloud. It can be Amazon Cloud, Microsoft Cloud, IBM Cloud. There are many providers here. But the transition to cloud is inevitable based on the need for this kind of heterogeneity of platforms and also the vast number of applications that lend themselves to different architectures. The other challenge that comes is historically, as you can see, this is an example where you have two things that are being sort of tracked. One is CPU utilization, one is memory utilization. And this creates the classic bin packing problem. Is some systems have CPU that is fully used and some systems that have memory fully used, but not both. Now, that's the situation with just two resources, which is CPU and memory. Now, just imagine how complicated this will become when you have many more resources to sort of manage, like you have an accelerator, you have non-volatile memory, and you have some GPUs, and you have some other specialized XPU cards or what have you. Making sure they're all fully utilized in a balanced fashion and being able to bin pack across them is a tremendous challenge. And the only way to get better at this is to have a diversity of workloads that can sort of fill in these gaps that are going to exist when you have multitude of resources that you need to schedule. And so these present some tremendous challenges and opportunities also. The other key challenge that when you get to the scale of cloud computing and warehouse scale computing is you have many applications and underlying platforms. And one of the questions that often comes is, I have this kernel change. Is this good for the data center? Or I have this BIOS change. Is this good for the data center? And oftentimes what you'll see is a pie chart. If you run various applications, some applications will see some benefit. Some applications will actually see some degradation. And the question you have to answer is this a good thing for the data center overall? Right? And you need a methodology to sort of inform those decisions so that you're making forward progress in an engineering-driven manner in which you can say quantifiably that, okay, this has overall improved the data center efficiency by such and such. Right? But it also points to an important thing is you need an abstraction which allows for flexibility of changing these controls dynamically. So for example, if application A, which is on the blue side, which is positive, you want to be able to leverage those changes. But if you have on the yellow or red side, which is sort of negative, then you want to be able to undo those changes when those applications are running in a dynamic fashion. So these are sort of fundamental issues that you have to solve when you are operating at the scale of data centers and cloud here. And this is a methodology that you can use. More details on this, I won't get into the details, but sort of getting to a weighted average of performance of the entire data center is an important way to sort of evaluate the overall metrics by which you consider changes that go into the data center. And there's more details on this in a paper which we call WS Meter. If you search for it, you'll probably find it. And the key point here is if you're making a change and the change has a 10% performance difference, then you may be able to verify that with, let's say, 500 machines. But if you, let's say, have a change that is making a 2% difference, then the number of machines you'll need to validate that in fact you're getting that 2% change improvement is much larger. And so you need a methodology by which you need to figure out what is the statistical sample that I need to be able to verify the changes that I'm trying to make to see if I'm making forward progress here. So the high-level message here is to be able to realize this kind of value from this wide variety of heterogeneous resources that are available and the wide variety of applications that lend themselves to different aspects of this heterogeneity. You need a very well-defined abstraction layer that hides all this complexity, but has the knowledge and the feedback loop to understand how to tailor the underlying system to better match the application needs, and also how to sort of fine-tune the application to better leverage the underlying hardware. Okay. So these are some of the industry trends that I've sort of tried to summarize. Is you have an emerging class of workloads, you have increasing heterogeneity in the fleet, you have the ability to match these applications to their more affinity platforms. But to really fully realize this, there is really no option but to transition to the cloud, which is where all this infrastructure exists. So no single organization will have the ability to provide infrastructure for all these different use cases. And since the use cases keep multiplying, leveraging the cloud where you can get the latest advances in technologies available to you is the most economical way to make progress in your field of discipline here. Right. And the key parts to sort of fully realize this is much improved abstractions that are needed to hide the underlying complexity. Okay. So what do these trends mean in terms for emerging markets? So the key conclusion that I want you to drive here is that the adoption of cloud will accelerate, and we are already seeing evidence of this from all cloud providers, is that their demand for services is growing, and that will continue to accelerate because the economies of scale help all users as well as the hyperscale providers. Right? There's also an importance for organizations to be able to leverage the latest technology. Right? Technology refreshes happen every year. And for users to be able to leverage this, the best option is to adopt cloud, where they can get these latest technologies available. Right? Otherwise, organizations usually refresh in 4 to 6 year cycles, which means you're not able to leverage the latest technology if you do not transition to the cloud. Also, organizations need to really focus on their core competencies. And what has been obvious is, computing infrastructure is a specialized area which, at scale can provide huge economies of economic benefits. But without the scale, you cannot fully realize those economic benefits. So it's best for organizations to focus on their core competencies and leverage the capabilities of the cloud to advance their goals here. The other thing is also to leverage frameworks to make it easier to adopt these new technologies. And I just list some obvious ones which have been developed, and there's a huge following on these frameworks. The open source community contributes heavily to these. There's no point in duplicating that. It's best to leverage it and speed up your application and infrastructure development. And the third is to make sure that the investments that you make is sort of easily transferable. It's very important to stick to open standards and not be locked down in any proprietary solutions, which may then sort of slow down your ability to accelerate to the latest technologies. So that's the first part of the trends that I wanted to capture in terms of infrastructure, how it's evolving, the heterogeneity, the need for abstractions, and the need for frameworks, and the need for recognizing the breakthroughs in machine learning and AI. The second part, I'll focus more on what these opportunities mean for emerging markets and why the time is right for emerging markets to embrace these. So one question that often comes is, why deep learning now? Deep learning has been there since 1980s. This ideas have been there for a long time. And what is different now is that at that time in 80s and 90s, the compute capability was just not there. Parallel computing had not advanced to the level it has now. Distributed computing had not advanced. Distributed software infrastructure wasn't there. And the data sets and the ability to manage that kind of data sets was also not there. So at that point, it took very long to train models, and the returns on those were not as much, which is why in 80s and 90s, this really failed to take off. But in the late 2008, 2009, it started to emerge as a compelling technology base, right? And especially with ImageNet results from 2012 that got published, the accuracy was far better than what even humans could do. And so that changed, and the computing capability had sort of advanced to the level where it was actually practically possible to train all those models. So that's why the timing is really right now. So compute capability has also become very cheap right now. You can get computing capability for a day on a GPU for less than $5 per day, right? So the capability and the cost has also come down. So these approaches now have become very practical for many use cases. There are large data sets now available, and people have understood the need to develop curated, ground truth, well-labeled data sets. Because if you have lots of data, very simple models work very well, right? And so As these data sets have grown, simple techniques have proven to be very successful here. And so the timing is just right for everyone to leverage this. In 2008, the National Academy of Engineering had presented a set of grand challenge problems, engineering problems, that all countries and especially the US should focus on. So this is well documented. The ones highlighted in blue are the ones that Google decided it would take the initiative on, and which is why I'll focus on those parts. The first is to restore and improve urban infrastructure. This is sort of how do we improve traffic congestion, how do we improve self-driving infrastructure so that not everyone has to have cars, and the amount of space that is lost in parking and all that can be sort of eliminated if you can have a self-driving infrastructure on demand. The other area is advanced health informatics, is applying computing to make medicine much more accurate, much more accessible to all, right? And also engineer better medicines, sort of using computing technology and genomics to do drug discovery and stuff like that. And the last part, which is engineer the tools for scientific discovery, which is sort of the frameworks that we develop and the computing infrastructure that we enable to solve these problems, right?
So, Dr. Rama, you had requested an alert when you had 20 minutes left.
Okay, thank you. I'll try and speed up a little. So this technology has had many recent breakthroughs, right, in computer vision, in language understanding with BERT models, and also language translation, speech recognition, events monitoring, and also self-driving infrastructure. These are some of the simple breakthroughs that you can say the last 5 to 6 years that have really transformed technology in these spaces. And these are things that emerging markets can leverage. These are solved problems. You can leverage these services. These are also being used. I'm not trying to market Google. I'm just using Google as an example. You can take any other company also. But AI is being applied in all applications at Google. And these are just some recent examples here, just illustrating the breadth of applications that can benefit from these emerging technologies. And also what you find is that the data is the foundation for AI. So one of the key messages to take is collect all data. It's always relevant. Make sure you time sequence it and save it and build infrastructure to sort of be able to add to this as you go along, because the more data you have, the easier it becomes. And so you can sort of see the various components that are needed to be able to manage data, organize them in databases, run analytics on them. There's tons of infrastructure that's already available for you to leverage. And TensorFlow is an example that of a framework that makes machine learning models or inference applications very easy to develop. There's a huge ton of libraries. There's also other frameworks like PyTorch. There's other higher level services like Keras. There's a ton of these that you can leverage, and investing in understanding how you leverage them is super important here. One key part that I do want to emphasize is an emerging concept called embeddings. And embeddings are a very powerful technique to encapsulate various aspects. And embeddings are just a vector of floats that you see to represent various things, right? And it could represent vehicles, it could represent images, it could represent text, it could represent medical images, it could represent anything that you want. You can encapsulate into an embedding, which is a vector of floats. And the way to think about this is it captures the characteristics of the object that you are trying to represent here, such that you can do arithmetic on these. And an embedding in a multi-dimensional space says that two embeddings which are close together in the multidimensional space are likely very similar, right? That's the characteristics, and the floating point values that make up these vectors are learned through a learning mechanism for these embedding functions. And this embedding is a very, very powerful technique because now you can do arithmetic on these embedding functions. So quick example is in text comprehension. So if you can represent text as embedding vectors, then you can do arithmetic like Berlin minus Germany plus Russia means you want Moscow, right? So this kind of arithmetic operations you can do, or king minus male plus female equals queen. So these kind of properties will hold on these embedding vectors once they are trained and learned properly to get these floating point values, right? So now once you have this mathematical representation, the closeness of two vectors in the embedding space determines how close they are in the meaning in real world. And that's a very powerful technique. This is used by ads and Google and in targeting ads and figuring out which ads should be shown to which user and what have you. And the embedding space can be multidimensional in multiple respects. So for example, in YouTube recommendations, there's an embedding vector that includes embedding of all the watch videos of a user, the user's characteristics, and how long they watch for, and all that kind of stuff, and the age of the user. So all that can be captured in an embedding vector. So this embedding concept is very, very powerful in understanding the behavior and relationships among various entities. And sort of for you to build recommendation systems or what have you, this is a technique that I recommend that everyone sort of figure out how to adopt. Very, very powerful and very versatile in its nature. The other idea that is sort of very, very important to understand is sometimes you can have computers train themselves, and the best example is AlphaGo and AlphaZero. AlphaGo is the Go playing system based on reinforcement learning, and AlphaZero is the chess playing system, which beat the most powerful chess engine at that time, Stockfish, in a 100-game series with 28 wins and 72 draws. And it trained itself in 4 hours by playing against itself. So this ability to sort of use the machine to train itself is a new concept, especially in the reinforcement learning models, where you have a sequence of events that each has a risk-reward kind of concept attached to it. So if I'm making a chess move, what is the risk versus the reward? If I can compute that, for any of those kind of models, this is turning out to be a very, very powerful way for the system without any data, just knowing the rules and playing with itself can train itself, right? So very powerful technique. And there are various ways that you can think about this. And I'm just using Google as an example. I don't want it to be a Google marketing presentation. But the way you can sort of approach this is you can build everything on your own with your own data, your own model. But you can also sort of apply your data to existing models, let's say from Google. Or you can sort of leverage Google's data and Google's models. So for example, if you have an image that you want to sort of classify or search for, you can sort of use Google service, or if you want to build your own service, you can build entirely on your own. All three models are possible. You can start with sort of leveraging what already exists and then figure out where you can add differentiation and build your capability. But there's a lot of stuff that already exists that I think merits sort of taking advantage of at this time. I'll speed up a little because I want to get to this part and I'm already a little short on time. I want to talk a little bit about the Indian context and how you can take advantage of these opportunities. So I mentioned the need for open standards, very, very important that you build infrastructure that is reusable and portable, very important just to protect your investment. I'll skip through here. Being cognizant of the principles, AI is very, very powerful and it could be used in nefarious ways also. So it's very important to have good guiding principles that govern how you go about it, right? To make sure you're not misusing any information, and if in case you get access to user data, how you sort of protect it so that it cannot be abused, right? Very, very important. Success in this space really needs, very good technology, and AI technology is super important. You need speed, which means you need very good hardware to work on and, access to accelerators. You need scale, which means you need infrastructure to develop models and what have you, which is available, let's say, through cloud. And then you need reach. And the best way to reach them is through cell phones, which is now becoming pervasive. So a pipeline and a functional flow that captures this entire space is important for long-term success. Example, and I won't go into details because this is just short on time, is an AI-first online grocery, Ocado, has sort of made it very easy for shoppers to get what they want and to alert them as to what they need with very high accuracy without even them realizing that they need those. So this is starting to become very popular as how do you sort of suggest and recommend what users need to do. Right. The three sort of high-level ways you can think about: you can build infrastructure, which is sort of used by everybody. That's very high value. Then you can sort of build AI building blocks and what have you to sort of serve your needs, which is, of course, then can be used by many. Or you can build applications. So just building the applications is easy, takes less time, but sort of as you go to the left-hand side here, obviously the value also increases here. There's a ton of open data sets that I encourage everyone to use. These are data sets that Google has made available to advance the state of the art in these spaces. If you can, please do make your data sets available. It helps the entire community. Make sure you prevent any personalized information from leaking out. Work through the anonymization tools that are available. But making data sets available makes it very easy to speed up the speed of innovation here. Quick example I'll give you is from IIT Delhi. This is something that students at IIT Delhi did. Is Delhi has a problem with pollution, and so they developed an app which students, graduate students there did in just less than a month by using the existing frameworks, by which they could take a picture from their cell phone and it would return to them what is the air quality for the day, right, with very high accuracy. So these kind of simple techniques are available to solve some really hard problems, and then you can determine, today do I really need to go out and do my shopping or go for a movie if the air quality is bad. Right. Another example is techniques to combat fake news, which is a rampant problem these days. And there are very simple models that can sort of figure out which tweets, for example, in Twitter are driving fake news. What are the keywords that sort of hint towards fake news? How do you sort of detect which users are contributors to fake news? All these are now within your reach to be able to solve and sort of figure out who you want to follow on Twitter and whom you don't, based on the ability to solve these kind of problems. Another example is sort of improved medical science, like I mentioned in the National Academy of Engineering Grand Challenge problems. Improved health informatics is an important area. And MRI, one of the biggest challenges with MRIs is that there's only some angles from which images of the brain can be taken. And there are parts of the brain where images cannot be taken very easily. But with current technology, you can sort of reconstruct what is inside the brain much more easily for the doctors to see. And this kind of capability significantly improves the ability for the doctors to diagnose what has gone wrong, and much earlier so. And the earlier they can detect, the easier it becomes for them to sort of treat those problems also. Traffic engineering is a big problem in India. I mean, I know traffic in India is crazy. I'm usually, when I'm sitting in a taxi or something, I'm holding onto the railings as though my life depends on it. When I was growing up in India, it never was a problem, but now I'm really scared sometimes. But there are many techniques that can help solve problems here. It's sort of understanding the traffic patterns, making drivers aware of where the challenges are, suggesting alternative routes, suggesting staggering times to sort of reach the various destinations to avoid congestion. Tons of very simple solutions can be made available in the space here. Okay. I won't go through the reading of this slide. I think I'll make sure the slides are available just so you can read through it later, just to save time. Another important area is, in India, cyclones and typhoons and those things happen all the time. And if you can sort of predict in advance where this is going to hit and with what intensity, with high accuracy, you can really save lives. You can really save infrastructure there. I was there in Vizag 4 years back when HUD hit, and it was devastation. For 10 days, there was no power, right? And people had to pump water through those manual pumps and stuff like that. So some of the things that you can now do is with high resolution atmospheric forecasting capabilities, you can sort of say, okay, where in my database have I seen this kind of weather pattern before? How did that change? Can I fine tune my simulation to get more accuracy? And can I say that which sections of the city will be hit most? And how can I take precautionary measures to avoid the damage here? So a lot of these are sort of very easily possible now with the available technology and should be applied here. Another example I'll give you is in India, there's a massive shortage of doctors, right? And I think deep learning can really help in this space. And there's one area where I think I'll be talking about a little bit more, but I won't lead through the slide, but I'll give you some examples. Is in predictive healthcare, can I predict, who will become a patient of what disease much in advance? In which case I can take preventive action, in which case I can prepare for them. And so much better healthcare is possible with many of these technologies. In the interest of time, I'll just skip through and speed up here. Another area is diabetic retinopathy. And this is the fastest growing cause of blindness throughout the world. 450 million people in the world have diabetes, right? So this is a big problem. And so what this does is regular screening helps, but access to regular screening is very hard. The equipment is sort of expensive, and getting the images and the expertise to read the images is very, very hard. So this is sort of the image of the back of the retina of the eye. And from this, the expert has to sort of detect if there is diabetic retinopathy, which means that will induce blindness. But if this is caught early, it's very easily treatable. The problem is it's almost never sort of tested for. So in India, there's a shortage of about 127,000 eye doctors, and 45% of the patients that lose their eyesight because of diabetic retinopathy never even get a test done, right? So if you can sort of make testing more available, and cell phone is the best way to access, and if you have a way of capturing the image of the retina with your cell phone and you can ship it to some center, and then the computer can then sort of run through it and say with high confidence whether this patient should get treatment or not, that will be hugely successful, right? And the interesting thing is, even with experts, so what happens is in these retinal images, they are rated between 1 to 5. 1 means there is no diabetic retinopathy, and 5 means you're almost blind now. And the idea is, if you can catch a patient at level 2 or level 3, you can prevent this problem, right? But doctors often, the experts themselves often don't agree on what categorization should be. Should it be 3 or 4, right? Or 2 or 3? 60% of the time, doctors will agree. 40% of the time, they don't agree amongst themselves. And if the same doctor looks at the same image, let's say after a month, they may come up with a different number, 60% of the time. So it's that difficult. But computers can sort of do this much more accurately now. So this is an area where applying this kind of technology can have meaningful impact on the lives of many. And so this is more details on this. You can sort of go through the papers here of how computers can do much better job of sort of diagnosing and root causing issues than even the experts in the space. So what I want to do is sort of summarize for you what I think are some of the key opportunities for you in the emerging markets. Is, there are many tools for scientific discovery here. Leverage those frameworks. There are many powerful frameworks here that are available. Leverage them to rapidly develop your applications. Create large data sets. So one of the key things is those that have the best data sets have the biggest advantage. So if you sort of invest in developing data sets and curating them and labeling them and feeding a pipeline of getting new data and incorporating that into your pipelines, you will come out ahead. Very, very important that you keep growing your data sets. And the larger the data sets, the easier it is to sort of build simple models that deliver the kind of accuracy that you need. And also to sort of think big and focus on some of these grand challenge problems, like this digital retinopathy has really transformed blindness due to diabetes, right? So those kind of challenges, if you try to solve, even if the sub problems that you solve there have huge impact, right? So I'm down to my last minute here. So I'll just sort of summarize the key messages that I wanted to convey in the beginning. Is that I hope I've convinced you that transitioning to the cloud has huge advantages. You really should jump at this opportunity. There's no point even debating it. The economies of scale just are overwhelming here. There is a need for clean abstractions because there's a vast amount of heterogeneity in the platforms, options, and also in the application use case. So making sense of this in a meaningful way without having to engage users to understand these details is very important, though, and clean abstractions can really help here. The deep learning has emerged as a very important area to solve some of the hard problems of our times, and it has proven to be very effective in bringing about several breakthroughs in this space. You should sort of figure out how you leverage the computing capability that accelerators provide now in cloud. Remember that good data is very, very important. The more data you have, the more data you collect, the pipelines that you build that add to this is very, very, very important. And when you build your systems, you should make sure they are sustainable functional flows, which means that as you are running inferences, whatever you learn feeds back into the models and adds to the data set so that your model accuracy constantly is improving. So I've sort of run out of time, and I want to stop here and take any questions that you may have.
Thanks, Dr. Rama. Wonderful talk, fascinating speech. I know I have an echo problem at my end, but we have some time open for a few questions. But I would request Shashi to be back on stage because you have to ferry people from the audience to the stage.
Yes, Dr. KVS has a...
Okay.
So, just a moment, I'll bring. The question is, on the problem of traffic engineering, one of the challenges researchers face is availability of data. Google seems to have access to having lots of data. Is there some way to collaborate with Google to get access to some of these data sets?
That's a good question. I do not know the answer to that part of the question. I can find out. But also remember that in the data that Google probably has is from US, which may not apply to India. So what you have is in India, there are these video cameras in all the posts in various cities, which are collecting this. So all you need to do is work with your local organization there to get access to that and sort of figure out what the traffic patterns are, study them over time, what are the diurnal patterns, what are the holiday patterns, and what have you. So a better approach would be to sort of approach your local city council and sort of see if you can work with them to get access to the video feeds from their cameras that they have installed everywhere. I'll find out if Google, the data sets that Google has made available, I shared in that slide deck with you. I do not believe it includes the US traffic system. I don't know the rules that are there, but I can find out if that can be made available.
Dr. Mohan also has one question.
Good morning, Dr. Rama. Very excellent and very comprehensive talk. My specific question is this: are there specific best practices and key heuristics that guide the hardware and software co-design that you spoke about with respect to CPUs, especially in the design and usage of frameworks like TensorFlow, etc.? Because as an application developer, should one be aware of them and how to best leverage them? Thank you.
Yeah, that's a good question. The question is, how do you do the hardware software co-design, especially for TPUs? And so what happens is, what Google does is it has a few key applications that are using a large amount of footprint and that are business critical. So for example, ads is one area, then translate is another very big use case, then visual search service, sort of classification and identification of images, and then the deep learning reinforcement models. These four, and the fifth one is the BERT, which is the natural language understanding. So these five are the key workloads that Google uses for its hardware software co-design. One advantage Google has is that we have the entire source code from TensorFlow application down to TensorFlow to the various compilers and runtime systems and the underlying hardware. So we can analyze this holistically from an end-to-end perspective for these five key workloads. And we use our hardware software co-design mechanism to optimize the underlying TPU architecture and design based on these five workloads. So more details on how we do this is on the published papers. There are two papers that have been published on TPU version V2 and V3. The V2 came in ISCA 2017, and the V3 came in the Communications of ACM last year. So if you search for TPU paper, you should be able to find these two. And that has more details on what aspects of the hardware software co-design went into informing the decisions on what should go into the TPU architecture. One of the fundamental things that we've learned is the precision numerics that is useful is we realized that actually multiplication can be done in what we call bfloat 16-bit floating point, as long as you accumulate in 32. This was a huge breakthrough in allowing us to go to lower precision arithmetic to significantly improve the performance of our TPUs. And Google actually shared this with the rest of the industry. That's why you'll see NVIDIA also has FP16 support now. But there are many aspects of the hardware software co-design, and I think those papers have more details. If you want more, you can reach out to me and I can help you with more there.
Thank you.
Hello, Dr. Rama, this is Gopal. A couple of quick questions for you. One is technical and one is more of a practical implication. The embeddings that you talked about, how...
Whoever's speaking, it's breaking up.
Can you hear me now?
Yeah, much better.
This is Gopal. The embeddings that you talked about, how different and how has this evolved from the whole idea of eigenvectors and that has been used?
I'm not sure. I'm not an expert on the eigenvalues and eigenvectors. Okay. But you can think of this as a representation in the multidimensional space. And having these floating point values that make up this embedding vector, we learn. And the way to think about these embedding vectors is in this multidimensional space, they're close together if they're related, right? And you now have the ability to do mathematical operations and extract meaning from these embeddings. That's turned out to be a very, very powerful technique in, many systems now. And, YouTube uses it, our ad system uses it extensively. So these embeddings are very, very powerful concept. And I'd failed to appreciate this earlier until my team was involved in the hardware software co-design, and when ads explained how they use it, it was shocking how flexible and powerful this technique really is. So I'm not sure about the eigenvalue part. Maybe some mathematics expert will have to help you there.
No, yeah. I'll go do my research. I was just curious.
Yeah.
Thank you. The other quick question I have is more practical. You talked a lot about this NAE grand challenges to set the stage with that. But how is the COVID-19 and this whole big transformation that's happening now? You didn't talk much about that. I'm curious, especially about how this changes the game for restoring and improving urban infrastructure. Because I think the notion of offices, homes, healthcare, education, everything is being questioned now in this whole wake of the pandemic. Any thoughts on that?
Yeah, that's a good point. I'm not fully on top of it, but I know that one of the things that has been leveraged, and Google and Apple are actually coordinating here because we make cell phones, one Android and iPhone. So what we can do is the cell phones can be a very powerful vehicle in doing contact tracing. So depending on, if somebody has been detected as having being COVID positive, from their cell phone you can figure out which are the other phones that came in close proximity to this phone, right? And send them an alert.
Yeah,
that,
we
hey,
actually had a paper on that presented yesterday in this conference.
Oh, okay.
On this very topic. Please continue.
Yeah. So what you can do is you can send an alert to those phones saying, hey, at this location you came in contact with somebody who has turned positive. It may be in your interest to get yourself checked. And after you're checked, please mark yourself so that we figure out how to sort of alert the tree that has to be informed. So that contact tracing and verification and closing the loop becomes more methodical. And that's one of the ways to sort of figure out how to leverage this kind of technology to solve these problems.
Thank you. Great talk.
Thank you.
Yeah, good morning. I'm Dr. Sanjay Chitnis. You mentioned about frameworks which are like TFX, etc., which are general purpose. What is your opinion on domain-specific frameworks which are coming up? For example, recently Andrew Ng announced Landing.ai, which is specifically for visual inspections. Right? So it will help collecting data as well as providing solutions which are specific to your industries. So what is your opinion in general about this?
So really, frameworks are only as good as how rapidly and how extensively they're adopted. One way to check that is, if you go to GitHub and then check how many people are contributing to it and how many people are using it. If there's a robust ecosystem around a framework, it'll be successful. So if only, let's say, 100 people are using it and 10 people are contributing, it'll be very hard for it to sustain itself. But let's say 100,000 are using it and about 10,000 are contributing, of course, it's going to be sustainable and it will flourish on its own. So that is a good way to judge, is this a framework that I can build for the long term, is to see, is there a community around it? Is there enough of an ecosystem that's growing around the space? What you don't want it to happen is that you build on something and then suddenly no one is supporting it, and now you are stuck with maintaining something that you don't fully understand. Right? That's one thing to avoid here.
Sure. Thank you.
Any other questions, comments?
Thank you, Dr. Rama.
Thank you for inviting me.
We can, excellent talk. Fascinating. We'll conclude the keynote, and next we move to the short paper track.
Yeah, so we end this session and we'll move to the next session. Thank you, Dr. Rama. Thank you.
Thank you. Thank you for inviting me.